Okay, so we're going to take a walk away from multipath for a little bit and talk about the very subject of the course, which is the effect of mobiles. Okay, so we're going to talk about the effect of motion on wireless communications. So let's say the transmitter is stationary, and the receiver is mounted in a moving vehicle. So in other words, this is you talking on your cell phone while riding in your car down 401. So the transmitter, which is the base station, is stationary. In that context, the transmitter is generally stationary, whereas you are generally moving. So even if you're not in your car, if you're walking around, you're still in motion. So the receiver starts out at distance d and moves at velocity v with respect to the transmitter. Okay, with respect to the transmitter is key here. So here's a figure for you. And this will be figure 1 in your notes. Oh, we've already gone through 2 equations for if you're following along. The first equation was the Rayleigh fading probability in the example, and the second equation was where I gave you the fading term in the two-path model. So what we're going to do is we're going to look down from space. So this is a top view. Here is my transmit antenna. Is transmitting EM waves isotropically out like that. And here is my car. And it is moving this way. So I can break down the motion of my car into 2 components. One component perpendicular to the antenna, and I don't care about that component because that's not increasing the distance between me and the transmitter. The other component is directly away from the transmitter like that. So just think back to physics when you talk about vector addition. You'll have a component that's perpendicular to the antenna and a component that is parallel to the antenna. This is the component that you care about, so that's v. And that v is velocity with respect to the transmitter. And what we're going to do is we're going to say, let's send pure sinusoid at carrier frequency FC. At the receiver, what do I observe? and this is equation 3. Sine, okay, usually it's sine 2 pi fct plus sine 2 pi fct plus, actually it's 2 pi fct plus d over c. But in this case, d is changing with respect to time. So in fact, we have the following: sine 2 pi fc t plus, okay, we start out at d over c, and we continue to move with a velocity v. So what's at any given time later? What's my position with respect to the antenna? How would I get that from v? V times t over c. And if we collect terms, so if we collect terms in t, what we're really interested in is any kind of oscillation, and that's any kind of phase that's proportional to t. So if we collect terms in t, we get this, equation 4, sine 2 pi fc 2 pi fct plus 2 pi fc, excuse me, that's not correct, 2 pi fct plus 2 pi v over ct plus 2 pi excuse me, that's right, that fc should have been there. 2 pi fc v over ct plus 2 pi fc v over c. This term I don't care about so much, but I can collect these, and I get sine 2 pi fc times 1 plus v over c t plus 2 pi fc d over c. So the frequency started out as fc and is now fc 1 plus v over c. So that could be greater or less depending on whether v is positive or negative. So I guess it increases going in towards the antenna, so the positive v is towards the antenna.
Excuse me?
Yes?
That 1 minus c raised to the power minus 1 is not part of this frequency there, right?
No. And this change in frequency you will know this better as the Doppler effect. One thing that this will do